Okay, everybody, we can get started. So I think I found some better settings to where you should be able to get my attention better in a chat. It should pop up a little bit better. Also, we have polling, where I can set out a poll just to see how things are going. All right, and just let me make sure all right, we're recording. So we're going to start a different tool. Okay, called Fourier, right? Where before we were doing Laplace. I guess the big difference is that in Fourier, everything is periodic, and Laplace is, non-periodic. All right. In some ways, Laplace is more complete, but sometimes that completeness can get in the way of what we're doing. All right. Now let's just, what does periodic mean as far as Fourier is concerned? Is that you're going to have a sine wave, right? But it existed, for minus infinity time, and it will exist for plus infinity time, where a sine wave in Laplace is really ut sine t, where it's off, and I'll just draw a small sine wave there, right? And that's time equals 0. So some things that we need to, we're going to talk about, and then why am I showing you this symbol, the prism, is that really we're going to talk about the Fourier series first, and not so much the transform. All right. And the series, and we're just going to just say intuitively, any all right. Any periodic signal can be broken up into basically a DC average or a DC part, right? And the sum of cosines and sines, all right? And each one of so the DC part, right, we're going to give it like fancy terms like A naught, or maybe even something called C naught. And we'll look at the equations later. But right now, I would just like to do this intuitively. All right. So if I take this signal here, right, does it have a DC offset? Well, you can see that it starts at 0, has positive area, right, and then it ends at 0, right? So if the period of this, right, and I'm going to just take it, I could do it slightly different, but if I say the period is from 0 to 6 seconds, what I'm saying is that then this shape repeats every 6 seconds. And so that's something, is that any signal can be made periodic if you just repeat it. So if you take your favorite song and you just keep repeating it and repeating it forever, well, you can take the Fourier series of it. And so that's just the assumption we're going off of. So the first thing is that it has to be periodic. That means it has to have a period. So one thing that you will do is you'll look at a signal and just determine the period. And so in this case, that's easy. It's 6 seconds. And then the first part is the DC offset, which is basically, or the DC average, right? And so that's really just all this area, but it's the average area from 0 to 6, okay? So you can do this with calculus, or find that the area of that triangle, the area of this rectangle, that square, this triangle, and so on. You can just do it like that or differently. All right, but that's really the first thing. All right, now there are things that can make it easier. Is that if I'm going to try to draw this over here, where I come up, flat, peak, flat, down, and call that 0 and 6. So it's got to repeat, right? Right. And so this signal is a mirror image of that signal. Maybe not the way I've drawn it, but all right. So that's even symmetry. And when you have, wait, no. Yeah. If I just repeat this, it's going to be even, because a cosine is like this, and you can see that it's the mirror image, where sine, all right, is odd. And the thing about it, if you can recognize if something is even or odd, you can make the math a little bit easier for yourself later. All right. So I'll just take a brief moment to see if there's any questions so far. All right. So before we just move on, taking the Fourier series is just like a prism. You take a signal and it breaks it up into the various frequencies. And these would all have various amplitudes. All right. So let's just do an example, right? So that Fourier series, right, it starts with a DC component, which we'll call today A naught, right? And try to determine it for this signal, right? And I can just see that 0 is here. And if I kind of draw 0 all the way through, right, it looks to be symmetric around the x-axis where, just by eye, this area is going to cancel that area, right? So in fact, A naught will equal 0, but there is a period, right, of 2 seconds, right, which means we have a frequency of 1/2 hertz, or omega equals 2 pi times 1/2, or pi radians per second. All right. Now here, if I told you that this is 0 forever, right, well, then it wouldn't be periodic, right? In fact, if I just said it's 0, the sine wave is active for a bit, and then it's 0, well, no, that wouldn't be, it wouldn't be periodic, all right? However, if I say t is from 0 to 10, and that it'll start oscillating again, and then, ooh, that's ugly, and flatten out, well, then it's periodic, all right? And setting the time is really important when we start to do our integrations, all right? And what's A naught here? Well, again, I'll try to draw a line through, and I have a positive area, a negative area. It looks the same: positive, negative, positive, positive, negative, positive, negative. And the negatives and the positives will cancel each other out. And so A naught again equals 0. Now in this case, I set it to the full length of the simulation. But in fact, I could choose this to be the period, or up to here, up to here. I can change that. So while well, I know you know how to do the integration of a sine or a DC offset. It really is good to be able to look at it and see if there's an area or no area. Okay. All right. So the equation for this, though, what is the equation for that average area, right? Well, you have the period and you have integration. And so a lot of times, I mean, you think about it, integration, people will call it averaging, and they'll almost use the terms independently, right? Because really, if I just scale it by the period or the number of samples, right, that's an average, but you still need the integration part. I'm sorry, there's some, are there any, is anybody distracted by a banging in the background?
It's fine.
Is it, can you hear it?
Yeah, I can hear it. But
Yeah, we can hear it.
All right, just go, hold on a second.
Oh shit.
He's regulating.
Okay. All right, well, it was distracting me, so. But thank you for being kind. All right, so.
No problem.
All right. So anyway, here we have, this is really just sine. I wanted to take the Fourier expansion of sine 2 pi t, right? Because hopefully if the Fourier transform or series takes any signal and breaks it up into sines and cosines, well, if I use it on the sine itself, I should get a sine, the original sine wave. So now as far as the area is concerned, right, again, the positive area and the negative area, you can, by eye see that that's fine, right? And, right, if you set this up, it's just 1 over 1, 0 to 1 sine. Okay, and you can get that, all right? You can go through that and find out that it's 0. Because sometimes it's not obvious. There's other things, and so you need to use that equation. But talking to Professor Morelos, who teaches 160, who uses this a lot, really seeing what the period is and what the DC offset is by eye is kind of an important skill. All right. So this term called A0 is 0. All right. And the period, period is 1. All right. So now this thing is, how do we go about finding these other coefficients? All right. Well, AN, so we're still doing our average. We're going to multiply it by 2, though. We're still going to integrate over the entire period. XT is the signal in question. Okay. So in this case, the signal is just a sine wave. All right. So the way we find all the coefficients of these cosines and sines is that we multiply by cosine. This is where the period comes in. And then there's n, and n is 1, 2, 3, and onward, right? And so they're all, it's all based off of the original period or the original frequency, all right? So if I have a 1 hertz sine wave, then the other higher order sine waves will be 1 hertz, 2 hertz, 3 hertz, 4, 5, all right? Now again, I don't actually, I can do this integration by I, right? I can see that that positive area goes from 0. That looks to be about 0.5. That's minus 0.5. That's the negative area, positive, negative. And that the areas, in fact, cancel out. So since this is, and I'll just write it out here, this is sine 2 pi t, that's xt, right, times cosine 2 pi t, and then I'm going to put a 1 here for the first harmonic, right? So that should give me a1. I'm just going to put that n there, right? So if I just integrate, right? This is generic for all the harmonics. This is just the A1 one, and I can tell by looking at it that it's 0. Okay. So far, A0 is 0, A1 is 0 as well. And in fact, we're always going to be multiplying xt by some function of cosine, right? And since we originally had a sine wave, there really should be no cosine waves at all. And so all of them should be 0. All right. Now this one looks much more complicated, right? We still have our original signal. I think you guys might not like that color.
Why was it that they're all 0 again? Sorry, I kind of missed that part.
All right. It's just in this, like in this case, right? Is that originally, if you think about it, and I'll rewrite it here, right? Xt, right, can be represented by some DC offset plus a sum of cosine and sine waves, right? So if our original signal is a sine wave, there's no cosine inside of it. No, you only are going to get one sine. So
okay. I thought the A naught was the DC component.
It is.
Okay.
Yep. Okay. I just went back to this slide to see the sine wave. Not, yeah. Okay. That's, gotcha. Yeah, all right, good. Good question, though. So in this case, we have, now what's being plotted is on the side here, but it's just a little hard to see. So the original signal, 2 pi t, now we're multiplying it by cosine 2 pi t, and the next harmonic, n is equal to 2. All right, and this is what we're getting. And it looks, kind of hard to see, but let's just, draw it down. And you can say, I have a little area here, one positive little area, another positive little area, but then over here I have a minus little area and a minus little area, right? I have a plus big area and a plus big area, and you can see that they all cancel out, right? Two little ones minus two little ones minus a big one plus a big one, it all cancels out. Now, sure, you can, the way to actually find A2 would be 2 divided by the period, right, in this. But notice, right, this is just, again, that's just area, right? And then that scaling 2 pi is just, that's what turns it into an average. And all we're taking is the average of the original signal sine times some cosine or sine when we do the b constants, right? That's all we're doing. And yeah, it's twice the average, which for this case, it's just take the number 2 and just kind of live with that. Okay. I mean, sometimes I search in the number, why the number 2, and then, days later when I have the answer, I realize, well, maybe everybody doesn't need to know that. All right, so now here we have, now we're going to find the b constants. Okay, or b, and there is no b0, it's just b1 plus b2, b3, b4, right? That's all we're going to find, right? Now, look at this. I go from 0 to 1, and yeah, the period originally was 1, but this is quite interesting because what is this? It's sine 2 pi t, which is the original thing, right? But now the first harmonic is sine 2 pi times 1 because n equals 1 t, which is really just sine 2 pi t squared, right? And notice it doesn't go back, it doesn't go negative. It's almost like when you're making that full wave rectifier for a power supply, right? It's almost, it's not quite sine squared, it's absolute value sine, but it gives you the same idea. And you can see that I have a positive area, right? I have another positive area, and then I divide by t to get the average, all right? Now, yeah, you might say, well, wait a second, it should be t divided by 2, but remember, it was the original period of the sine wave that we have to keep track of. Otherwise, we'll be off. All right. So our B1 is, it looks like it's 1. The math is down here. All right. Right now, I'm just trying to get across the idea of the areas. Now here, this is B, what is B2? Right? So we have our original signal, 2 pi t, right, times sine 2 pi 2 t, because now n is 2, right, and we're getting this shape. We draw a line through the area. And yeah, it looks like we have a positive and a positive and a negative and a negative, right? Now, yeah, for this one, it's pretty easy to see by eye that the areas are canceling out. Or if they didn't, the coefficient would be so small as to be meaningless, all right? So now down here, so that would be the intuitive way. But if we say generically, I have an omega naught, right, which is based off of a period, right? So this is like for a generic period. Xt is a sine wave, and it's any generic sine wave. I haven't set what the period is going to be. So to find the average of that, in other words, a naught, 1 over the period, integrate from 0 to the period, I just put in here, right? It turns out to be minus 1 over the period times the period divided by 2 pi, and you find out that it's 0. All right, so you can see that you really got to have those periods in there. And yeah, since you're eventually got to get a number, anything that's like a variable has to cancel out. All right, then we take a1, 2 divided by t naught. All right, sine times cosine. You go through the transformation and you get cosine 4 pi. Because I don't know if you noticed, was that this was sine times cosine, and the period went from 1 second to half a second. And so this shows up here. So this period went from, it doubled the period. And so the thing is that you can show that now if n is, integers, it's always going to be 0. Then for B1, right, we actually get 1. And then for the B2s, it's fairly easy to show that B2 is 0 and all the other ones are 0. All right. So that's kind of like an intuitive way, like, of the process, right? So this is a little more formal. All right. Is that if I can take any periodic signal and break it up into an infinite series of sines and cosines. Okay. So in this case, it's a DC voltage. And I'm sorry, somebody's at the door. So that was a sine wave. All right. So what would we get? what would be the Fourier expansion if I just had a DC signal, which takes a little kind of a trick to actually analyze it, right? So what you do is you say it's DC, but the period is, and I just made this up, like 5 seconds, right? So I'm integrating this DC from 0 to 5, and then I scale it by 1/5. And so essentially, this was 1 volt, I get 1, right? Now I could have done it. Sorry. So I could have taken it to 2. I could have taken it to 2 seconds and just scaled it properly, right? Now, another way to think of it is that so what is omega naught? Well, that is the period really 5, 1? Well, if I take that period and make it infinite, omega naught goes to 0. And so there is no, basically, the frequency is 0. And I can see that, this is not moving, it's DC. So therefore, really, there can be no sine or cosine. And so if I'm integrating any sine times a constant, right? So what is my xt? Is 1. I multiply that by right? Sorry, that's just omega naught t n 1, 2, 3, 4, right? So I'm just multiplying it by a constant. Well, the average of a sine wave, right, as long as I'm going through the whole period, is always going to be 0, right? So that I can say the bn's, right, 2 over the period, those will always be equal to 0. And then the an's, right, 2 divided by the period to the period cosine, right? Those will all equal 0 because I'm always, no matter what the frequency of the cosine, average is always going to be 0. Okay, and this is just really showing you these absolutely simple signals that the Fourier series works for a DC and a sine wave. All right. Any questions so far? Okay. So let's just go through, all right, and look at our first periodic signal, and we can see that the period is 1, right? So omega naught is 2 pi divided by 1 second. That's 2 pi radians per second. And it's a sine wave. And as our previous example, right, there's only one sine wave. That will be the sine wave where the frequency is 2 pi radians per second. There's nothing else there, so everything else will be 0. So yeah, it's kind of by inspection. All right. Here we have another periodic signal, right? And the period is just a half a second. So that doubles the frequency. So again, everything seems fine, but I notice it's going from 0 to 1 here. Before it was -1 to 1. We've raised it up, right? We've raised this up by a half, and that the original sine wave was 1/2 was its amplitude, so that we can look at it and say, all right, A naught is 0.5, B1 is 0.5 to get the sine wave right. And then that is that by inspection. Now, this signal, right, is a square wave going from -500 to 500, and we can see that the period, right, the period is 2 milliseconds. Now, this kind of shape, right, you know, that's that shape, and we're talking about sine waves and cosines, and it like, you know, how is that? It might seem like, how is that possible to go from square or to start summing up sine waves in a DC offset, right? Well, let's just put one in it. So I put a sine wave inside, and it's got the same period, right, as the square wave, right? And then you can see that there's no DC offset there. All right. And let's just kind of draw the, okay. So I'm not taking the average of that, right? I'm just trying to say, here is a sine wave. Let's just say I want to approximate this rectangular wave with one sine wave, right? And what would the area be? The error, right? The green is the waveform we wanted, right? And the blue is what we're giving it. And this kind of dark red, you know, right at this point, it matches. But here, the sine wave is underestimating it. It's underestimating it here, right? And so if I didn't care so much about the error, I could approximate this with one sine wave, right? Now here, you can see the DC offset, right? That's 0, it goes to 1, and it's on half the time. So A naught, the period is 2 milliseconds. We integrate 2 milliseconds. And in that range, well, this is the xc/dt. But notice it's 0 for half, right? So that's really 2 milli, 0 to 1 milli, 1 t, right? It's like those RMS problems where you've needed to find the RMS, right? You had a half wave rectifier, right? And rather than finding the integration for the whole period, you just broke it up into where it was non-zero area, right? And that turns out to be plus 0.5. All right. And again, here we have a triangle wave. The period is 1 millisecond. That's about 0. And you can see that those areas are canceling out. and A naught equals 0. Now, so really, well, that's not good. So if we, okay, so in the homework, right, question 1, find, for each waveform, find the DC average in the period, all right? And so this is going -1 to 1, 0.5, minus 0.5 to 1.5, right? Here, everything is greater than 0. This is it's a square wave, right? It's on for about, let's see, the period is a millisecond, and it's on for 0.1 millisecond, right? So it's on for a tenth of a period, and it goes up to 2.5. Here, it looks like it's at 50%, that's 75, right? And so you should see, you can use the equation, or you can just kind of, that's a box area divided by the period, and you'll have A naught, right? Then here, I just give you an equation. Now this one, yeah, you're gonna need to use the mathematical models. So we have sine squared, right? And we have sine cubed. And then I talk about various filters, okay? But I mean, this is, we're not gonna learn how to do all the homework problems on one day, all right? Sorry, somebody emailed me. Maybe they're having trouble with the lecture. Somebody's having trouble. All right. Okay, we do have 50 participants though. Did anybody have trouble logging in to begin with? Oh, I got a chat.
I think people were having trouble because they keep trying to use the one that's repeating on the dashboard of Canvas, but that's the one that doesn't work.
Oh, it didn't delete it?
No, it did not. It's still
It's also
accessible.
on calendars. So you have to search through the inbox for the new one, and I don't think a lot of people realize that.
At first.
Every
We're up,
week,
we're
probably,
up,
there's a couple people.
we're up to 50, although we're supposed to have all right. I mean, since it is recorded, I'll have to, I guess I have to go and see if I can somehow delete that old meeting from the calendar. But I don't want to debug this now. I'd rather just get back to them. So next time, I will show you how to calculate some spectrum, you know, in a very formal way, right? But let's turn back to like what it is we're doing and why, all right? And so like I said before, the Fourier series, we just take anything that's periodic and turn it into sines and cosines. And so we can do square waves, all kinds of things. And you can even do circuit analysis. But reading through the examples, I think it's better to just do the circuit analysis the way we do it in Laplace. And then when we're doing the Bode plot, that is like the Fourier transform of everything like we've done before. And so this kind of summing things up, what it's really good for is finding out what things are there, all right? So there's three ways I can break it up. I can break it up into sines and cosines, but then you can also break it up into cosines, and basically you have a phase, right? If you only want to use cosines, you can come up with the phase. And then there's even the exponential form, right? So where can this be useful? This is an old project where you would put your finger on the sensor, and your heart rate changes the pressure, thus the index of refraction in your finger, and that sensor can pick up on it, and then you have an op amp, you filter out what you don't want. And this is actually, this is kind of close to what you would see, even though what I really did is make a triangle wave and put some noise on it. And so if I want to filter it, what I want to do is do the Fourier series on it to see what are the frequencies. Now, sure, the main frequency, you can see it's repeating every second. So, you know, your own eyeballs are a Fourier transform or a Fourier series. All right, but what else is there, right? So in this case, the DC component is removed, right? And the 1 hertz, right? That's the actual heart rate that we're looking for. But notice I've zoomed in on it, but it's 1.702. You know, it's going up by like 10 millivolts, right? The signal's quite small, right? So I need to amplify it, but I also need to get rid of things that I don't want, right? So how would I do that? Well, here's the 1 hertz is what I wanted, right? And then these other parts I don't want. So if I want something and not the rest of it, well, that's a bandpass. Now I've drawn it like a rectangle, which you can't really have, right? That's not a realizable filter, but it is saying this is the part that I want, okay? So on an exam, if they would say, what kind of filter would I want to keep the 1 hertz signal, right? You could, yeah, you could draw a shape like this, right? Or I'll draw it over here. You can draw a band pass like this. But really, even this, even a rectangle saying this is the part that I want is all you would need to do. Okay. Now, here we have a half-wave rectifier that I'd been talking about. And here's a sine wave coming in. And then, yeah, I just programmed it rather than using a diode. All right. So here is the V in. Then I've done a half-wave rectifier, right? And you can see that this is my V in, and I'm getting, you know, pure sine wave. And then when I do this rectifying, I start to see these other harmonics. Now I might have, well, we're going to learn how to use these equations to come up with expressions for a Fourier spectrum. The fast Fourier transform just does it, it does it numerically, all right? And so this is the half-wave rectifier, but I want to turn it into a, I only want the DC, all right? So in fact, the DC is removed, right? This, you can see it goes from 0 to what, about 3, right? When you do a fast Fourier transform, it automatically gets rid of the DC for you. So in fact, the part of the signal you want, you can't really see. So what do you want though? You want a low pass, right? Which I can draw like that, meaning I don't want the higher order harmonics. I want these to be reduced, right? And so this harmonic, right, from here, it's, you know, it's about, you know, it's on the order of 0 dB, right? But when we, but notice this is after it's filtered, right? It might look like a sine wave, but notice it's got a DC offset of about 1, and it's going from 0.81 to a little bit to 1. So there is still a sine wave there, but it's much reduced. And so even, like I said, the DC's been removed, and now this peak after that first filter is below 0 dB, right? And then I put it through another low pass filter, right? And it's below minus 30 dB. And so even though it looks like the sine wave is still there, look at the scale. This is 0.986 up to 1.01, right? If we were to plot this from 0 to 1, it'd be kind of hard to see that ripple, right? So this is just a different way of looking at the you know, that half-wave rectifier circuit from, you know, your original circuits lab. And this is just a low-pass filter and another low-pass filter. And yeah, I just was chaining these together in like a kind of a cheesy way. All right. I think the rest, we don't need that. So if we're going to calculate the coefficients, and this is a 50% square wave, all right? So whatever the period is, it's only on for the period divided by 2, all right? And so if we were to formally calculate A naught, 1 over the period, 0 to the period divided by half, because it's 1 on that time, right? And for the other part, it's 0. The periods cancel out, and we're left with 1/2, all right? For the cosine, right, again, this is 0, right? And that's t. The way I've drawn it is this is an odd function, and there really should be no cosine terms, right? Because ANs are cosines, BNs are sines, all right? So, but still, I set it up. 2 divided by the period, integrating over the period. Now again, I only integrate to half the period because all the other times it's 0. Now, if this was on for 3/4 of the period, oh, will it be the same if it's not a 50-50? Right, so I was just kind of saying that. So let's say AN, or let's go to A naught, right? The period is still the period, right? But what if it was on for 3/4 of the period, right? Well, then I would change it up here to 3/4 of the period, right? And in this case, it's 1 dt, right? Now, if I'm finding the A naughts, this part still remains the same. This would then turn into 3/4, right? Or if we were doing that homework where I said it was 1/10 of the period, this would turn into 1/10 of the period. So really, this number changes, right? And so you see you get sine, so sine of 0 is always 0. And then sine of this, right, of half, it's always at half. Whether it's at the first, second, third, fourth, whatever harmonic, it's always 0, right? This will always be 0, so it's 0 minus 0. Now here, the BNs, right, we have the sine. That turns into, we're evaluating cosines, right? And we get the -1 here. And then notice, right, sometimes we just have to draw it out, right? The cosine, what? It starts at 1, goes to -1, and ends back up at 1, right? So this is always -1, right? If this is, so it depends on what n is, right? If it's giving you a full period, it'll be 1. 1 minus 1 would be 0. But if you're getting half a period, right, it'll be 0. 0 minus 1, minus 1 times minus 1, it gives you a constant. And so what happens is you only get the odd coefficients. So Bn would be 2 divided by n pi, but subject to n equaling to 1, 3, 5, 7, 9, 11, 13. All right. So okay. So why is this important? While we do spend, 110, we're continuous time systems, right? But you might be thinking that the whole world has gone digital, right? Well, microcontrollers are controlling, I'm going to redraw it over here, right? Microcontrollers are digital computer chips, right? But they take sensor inputs, right? Could be temperature, right? Pressure, and these can all be analog, right? And there's an analog to digital converter inside. So you can take all that analog input, put it in the microcontroller, and then do what you want with it. But then sometimes it's got to control I'm not a very good artist. Here, let's just do a autonomous driving vehicle. Okay. And that's in the real world, right? Real things are in general controlled with analog signals, right? So you need a digital to analog converter, right? But if you remember from your 118, right, this would be like a digital signal, right? Right, it's 0 or it's 5, it's on, it's off. So microcontrollers have these pins that are sending out digital data, right? But if I take a 50% duty cycle and put it into a low pass filter, right, I will get a 0.5 signal out. That's DC. Now it'll have a little bit of ripple on it, right? If I put in, I'm trying to draw 3/4, put it into a low pass filter, right? I'll get an average value of 3/4, right? And so what I can do is actually change how long I'm on over time, right? And kind of, let's say I wanted a triangle wave, right? If I zoom in on that and I'm taking it out of the low pass filter, I could have a DC here, then I step it, then I step it and it's DC for a little bit, step it for DC a little bit, step it for DC a little bit. And if that little bit is very, very small, it'll look like a straight line. And so this is a pulse modulated DAC, right? which is at the fundamental heart of it, is a low pass filter. But there's a lot going on. You just don't put an R and a C together and have it work out, right? So in fact, this is the final project in lab where you will make a PWM DAC. You'll choose the kind of filter, the cutoff frequency, all these things. And so this is just the first taste of it. All right. Any questions? Yeah, shoot.
I have a question.
Oh yeah,
So-
yeah. Ask.
So for all these, the averages is basically A naught, but you're saying we can also just I it for a lot of these functions?
So I guess there's two things, right? Is that when I'm learning something new, right? And you show me these, like here's this equations, right? I don't think I have it in those notes, but I'll just describe it. Is when you look at the equations for the Fourier series expansions, right? It can be a bit daunting. Like, what does this mean? What is going on here? And really, so the reason why I would want you to do it by eye is so that when you get into the actual mathematical manipulation, where you're kind of just grinding out an integration, if you know roughly what kind of answer you're supposed to get, you'll kind of know that you're not getting it. You know, the answer you come up with, if you make a mistake in your math, is wrong, right? So if you can tell, like ahead of time, you know, I think these areas will be zero. I think they'll be non-zero, right? It'll truly help you understand what's going on with whatever particular signal you're analyzing, right? And so that's kind of why I want you to be able to do it by eye, but then recognizing that you're really just finding an average, right? And and sometimes when I say this, people might take it a little bit the wrong way, where I'm not saying you should know this. I'm not saying that at all. I'm just saying, remember your RMS. Oops. All right. RMS. Well, okay. There's a square root. The A naughts, right, don't have a square root, right? You have 1 over t. The A naughts have 2 over t, right? And the B naughts have 2 over t, right? You're integrating. Hey, we're integrating. We're integrating here as well, right? Here, though, it's xt squared, right? Here it's xt cosine n 2 pi f t. Oops. Okay. And that when, oops, I'm sorry, this is sine. And that when xt was sine, and this was sine, and we were integrating sine squared, well, that's just like finding the RMS value of a sine, because sine squared. Here we don't scale it by a factor of 2, and then we take the square root, right? So I'm just trying to remind you of the fact that you're not learning it's not as new as you think, because there's something called the cognitive load theory, and it's basically if you too much gets thrown at you at once, you won't remember any of it. So you try to remember things that you've done before, to keep your cognitive load down.
It's like information saturation.
Yeah, that's another good way of talking. And I realize that 110 lectures are probably information saturation every day, all day.
Yes.
I get it, right? So, any other questions? Oh, well, did I answer your question?
Yes, I actually had one more though. So why do you have to have the average for the A naught? Because I kind of saw for square wave, but I'm not sure. Does that same concept apply to the sine waves?
I guess the thing is that these equations are the definition of these coefficients, right? And yeah, you do have to find, notice, because we're finding an average, right? That means we're coming up with some kind of number, right? Here, no matter what the frequency is, right, we came up with a number, right? No matter what the original frequency is, we come up with a number. And so that averaging, right, and the fact that we're integrating to a number, we're not creating functions of time, that, yeah, it really is the average for any signal. Whatever xt is, ANs will always be found by multiplying it by higher orders of cosine, and the BNs will always be found by multiplying the original function by higher orders of sine. Did that answer your question?
I was like specifically asking why for A naught, or why it would be half of the other coefficients. Like it's just, is it just is there like this particular way that it works? Like, was it the same as a square wave, or like because that it looked like it was one function for sine. I'm not sure why for it would apply beyond just square waves.
You know what? I think what I need to do is show it to you. Like, we'll review the square, right? Next time we'll do other periodic waveforms like that, and I'll just have to show it to you. All right?
Yeah.
Because, I mean, A naught, right, it really is just the average, right, of whatever xt is. And in this case, the average, it was 50% on, so the average is going to be 50% of whatever that value is, right? Here, right, I have this area and then that area, but I have to divide it by the total period to get the average area, because while this area is positive, this area is 0, I have to add them together. Did that help?
Yeah, I think I'm just having a hard time picturing for the sine and cosine waves. But yeah, no, that makes sense.
All right. I think really next time, this was just kind of getting your feet wet. All right. And if you can look at a signal and determine the period and the DC offset after today, that's all today's about. Okay. And we'll get the rest of it next time. Anything else? All right. Everybody have a good rest of your day. I just want to say, though, is if you're having trouble, just email me right away. And even if you ultimately solve your issue before I get to it, I don't mind, right? You can always just send, oh, hey, professor, don't worry about it. I figured it out. All right. I'm really here to help. Okay. Anyway, have a good evening.
Thanks, Professor.
All right.